So because we talked about distortion, which I wasn't planning to cover, I'm going to skip opinion dynamics, which I was planning to cover. And instead, I'm going to focus this one on sort of some continuation of what we just talked about, some distortion-like things. And I want to introduce market-based approaches. Okay? And so for that, we'll need a very quick primer on what market-based approaches could be and what market-based approaches really mean. And so voting is basically one person expressing their preference about what should happen. Okay? And a market-based approach could be you are expressing your preferences about what should happen, but in response to societal preferences. So the way markets work is that you get a price signal. A toothpaste costs a certain amount. That comes from supply and demand. You respond to that price signal. So you're not individually negotiating with everybody else saying you want a toothpaste, you want a toothpaste, you want a toothpaste. You're responding to a price signal, and then the collective responses to this price signal then set the price. Okay, so that's a basic market-based approach. Another way of thinking about a market-based approach is where you're directly negotiating with people. Okay, and we'll see an example of both. Okay. And for that, I want to give like a quick introduction to what I mean by these market-based approaches. Wow. Okay. So one approach that's going to be useful is going to be Nash bargaining. Okay. So Nash bargaining is the following phenomenon. Imagine that there are two individuals. Okay. There are two individuals A and B. Okay. Let's imagine that there's these people have to bargain about something. Okay. They have to bargain. There's some pie. Let's say there's some cake that they're trying to split. It could be anything abstract. They have to bargain about something. And let's assume that if they don't actually agree, then they both get utility 0. And this is called the disagreement alternative. Okay. And so if they don't agree that they're trying to do some A and B are trying to bargain, they both have to agree on an outcome. Okay? It's like someone is trying to sell you something. If we don't agree, there's no sale. So it has this notion of voluntary participation. Anyone can walk away. If either of them walks away, then they disagree, then they both get utility 0. So this is A's utility, or you can think of this as negative cost, okay, or reduction in cost, and this is for B. But if they agree, then they can potentially achieve some region, and let's say they can achieve this region. Let's assume this region is convex. Let's assume that you can run randomized lotteries, which ensures that the region is convex. Okay? And so this is the basically achievable region. Okay? So if they agree, they can achieve any point in this region. Now, how do you know which point should they? Just looking at this curve, how would you know what's a fair point? How should they bargain? So if we were to axiomatize it, let's say they end up choosing, let's say they end up bargaining and they end up choosing this point A comma B, which gives a utility of A to A and B to B. Okay? Can you somehow axiomatize, say something about this utility? So the deviation here is a little bit funny, because if A deviates, then they'll go to 0, 0. Because let's say the strategy space is that A says, okay, I'm happy with the solution. Let me call it X, Y instead of A, B. let's say that A says I'm happy with x comma y, and B says I'm happy with x comma y. If A disagrees, does anything else, they haven't both agreed, then you immediately go to 0 comma 0. And so pretty much any non-zero point here would be a Nash equilibrium. Okay? Because the strategy space for both of them is to propose a solution. If they both agree on the solution, then that happens. So any point here is a Nash equilibrium. Any point strictly which is not 0, 0 is a Nash equilibrium. So it seems like so the suggestion here is that maybe a reasonable thing to do is to say that this has to be Pareto optimum. Okay, so if you were to axiomatize it, you could say that it has to be Pareto optimum. Anything else? So there are some people who are very squeaky. They'll say, well, this is very important to me. There may be someone who might say, oh no, this is not the utility curve. The utility curve looks like this because this thing is super important to me. Somehow somehow it should be invariant to affine transformations. So I should not be able to just double my utility for everything and get more. Right. So currency should, the numerator in which I measure utility shouldn't affect the outcome. Right? Does it make sense? So it should be invariant to affine transformations. Okay. Yeah, the disagreement point will also, because the disagreement point is fixed not in terms of utility, but it's fixed in terms of what actually happens. So in fact, I could have defined the disagreement alternative as being x prime comma y prime, and then this would have been x minus x prime y minus y prime. Yeah. Sorry. Excuse me. Okay. And then it has to be symmetric, which means that if I change what I'm calling A and what I'm calling B, it shouldn't really matter. Okay? Sorry, what's the question? No, so yeah, so the question is why should it be symmetric? No, symmetry here means that if you interchange what A and B are. If I were to flip the axes around, so if I do a 45-degree rotation, then this would, if this was the earlier solution, this should now become the solution. Yeah, so it's sort of, it should be invariant in a relabeling. And the fourth should be that is independence from irrelevant alternatives. Can someone guess what that would mean in this setting? Independence from irrelevant alternatives? Because they know, like, it's not a ranking setting, but the name is the same. Okay. What that means is that suppose x comma y is what you end up choosing. Okay. Then if I were to, let's say x comma y is the outcome of this bargaining. Then if I were to chop portions of the utility space, if I were to say, okay, this area here is not valid anymore, okay, then x comma y will still remain optimum. Because I chopped up feasible portions of my feasible region which were not being used anyway. So it's a matter of, so the way these Nash bargaining, this bargaining problem is set up formally is you're allowed to run lotteries over solutions. Because you're allowed to run lotteries over solutions, you can automatically achieve things in the interior, because you could say with some probability we're going to disagree, with some probability we're going to agree. Or with some probability we're going to choose this and some probability we're going to choose that. So it automatically makes the entire region convex. So maybe I shouldn't have drawn this like this, maybe I should have drawn it like this. Yeah, sorry. Yeah, yeah, yeah. Yeah. Sorry. The fourth point is the independence from irrelevant alternatives. And what that means is if I take away, let's say this is my utility, my feasible region for my utility, okay? And let's say this is the point that I choose. If I chop off regions of the feasible space, okay? So this might be, for example, a cake cutting problem, and the utility depends on how much cake there is available. And maybe I take away some of the icing on the cake, and some regions of utility are not available anymore. So let's say my utility region now looks like this, as opposed to that. So I chopped away some of the feasible region from my utility space, for my achievable region. But I didn't chop away the optimum, the outcome of the bargaining. Then the outcome of the bargaining shouldn't change. Okay? Just because yeah. Yeah, so if I remove a part, if I remove a part of the utility space, so there are some solutions, some feasible solutions which I remove, which were not which are not going to be the outcome of the bargaining, then it won't matter. So let's say you and I bargain. I say, okay, you take half the pineapple, you take the pineapple part of the cake, and I take the orange part of the cake. Okay, and so that's what we agree on. Then someone comes, your mom comes and says, no, you cannot. One person has to take exactly one piece. You can't take half pineapple, half orange. I can't take half pineapple, half orange. We weren't doing it anyway. So the outcome of our original bargaining problem shouldn't change. It shouldn't be that I shouldn't come and say, oh, I now want pineapple instead of orange. So if you take away portions of the feasible space which were not the outcome of the bargaining to begin with, then the bargaining outcome shouldn't change. Okay. And so in Arrow's theorem, this was somehow, in my mind, the weak point of Arrow's axioms. But here, this is a very solid, it's a very solid axiom when it comes to bargaining. Okay? Like you and I were going to bargain and get to this point. Something else which you wouldn't have wanted to do anyway, some option gets taken away, it shouldn't matter. Okay? So as it turns out, there's a unique solution which satisfies there's a unique solution which satisfies all four axioms, and that's called the Nash bargaining solution. Okay. And the Nash bargaining solution will say that you want to maximize log x plus log y, okay, where x is the extra benefit that A is getting over the disagreement alternative, y is the extra benefit that B is getting over the disagreement alternative. You want to maximize the sum of the logs of the two. Okay. Does that? Yeah, so x and y are the utilities. No, the outcome, this is the only solution. If they were to pick, let's say that even though they're bargaining. Oh. X over x and y in the feasible set. So this is not the strategy space, this is the actual solution. The question is, what's the strategy? So there's no strategy space here yet. This is the full solution. Okay. You have to, so the question is, so there are two things here. So the question is, well, how this is implemented? Is there an underlying Nash equilibrium? And so unfortunately, Nash did too much stuff. So since Nash did so much stuff, it's like hard to not think of Nash equilibrium. But this is not there's no claim here that this is a Nash equilibrium. Okay? This is the unique point. If you maximize this, you'll get some x and y. And this is the unique way to satisfy these 4 axioms. Okay? How you implement them? How can you design an actual game? So it's the outcome of the game ends up being this. That's a separate research problem. Okay? So, and remember this x is the difference from the disagreement alternative. Okay? So just remember this function, because this function is going to make an appearance again. Okay? Sorry? Yeah, sorry, it's the same thing. Yeah, it's the same thing. This is the D is a disagreement alternative, which I assumed is 0, but it's like the difference. Yeah. And the maximizing the product and the sum of the logs is the same thing. The reason I want to write the sum of the logs is because it's going to connect to the next thing I'm going to do. So this function, unfortunately, or I mean Nash did too much stuff, so I mean it's not unfortunate or fortunate, but like this function is also called the Nash welfare function, which makes it even more confusing that there's a Nash bargaining, a Nash equilibrium, and a Nash welfare function. Yeah? So does the bargaining thing make sense? So how is this connected to markets? So by the way, bargaining is a very general concept. You could do bargaining for anything. Okay? Markets are a more specific concept. And what happens in markets is that imagine that you're given some goods. Okay? You're given some goods. Let's say you're given goods G1, G2, Gn, okay, and you're given, so let's say Gm, you're given n buyers, each with $1. Okay. And these dollars could be fake dollars. Think of this as monopoly money. Okay. And these buyers then, and these goods have prices. Okay. So each good, there's 1 unit of each good. Each good has a price. The price here could be P1, P2, PM. Okay. Now, given these prices, what would if each buyer has $1, what would the buyer do? The buyer would go and buy the bundle of goods that gives the buyer the most utility. Okay. So I'm going to say Uij is the utility of buyer I for good J. Okay. And so if the buyer gets xi, if the buyer gets an amount xij of good J, then the utility will be Uij xij. So it's going to be linear. Okay. So I'm going to assume the utilities are linear. Does that make sense, or should I write it formal? No, I mean, yeah, I don't know. It could be good, it could be bad. So the question is, why is linear a good utility? Yeah. So I think, so this is mostly for illustration. The theorems that I'm going to mention, the market-based approaches, they work with pretty much all utilities, but some theorems only work with linear utilities. So for now, I think of it as mostly illustrative. Yeah, there's no utility, they have no utility for money. So the problem that each buyer is solving is to maximize summation over all j of xij uij, yeah, subject to summation over all j xij pj less than equal to 1 and x greater than equal to 0. It could be to take the maximum Uij, but that might not exhaust all your U. The question is the solution not to just take the maximum Uij? Yeah, that could be the solution. It might not exhaust all your money, okay. In which case you might go and get some more. Oh, sorry, you also have to have xij less than equal to 1, sorry. Any individual cannot buy more of a good than actually exists. Yeah. So this is what the user is going to do in response to these prices. And there's a beautiful theorem by Arrow and DeBrew, which says that in this setting there exist prices such that when every user makes their optimum decision for themselves, every good gets sold exactly. Okay? So these are called market clearing prices. And so, when I say market clearing prices exist, what it means is that there exist some prices P1, P2, PM, such that if every user comes and buys their favorite bundle according to these prices, right, there's some solution to each of the user problems, so that when you stitch them together, the market clears. Okay? And it's one of the most non-trivial theorems in this area.
It's not necessarily either 0 or 1. You're allowing people to buy part.
Yes. Yes, it's neither 0, yeah, Xij need not be exactly 0.
But is the summation over the users because there's a capacity for each user?
No, so each user is ignoring, each user is not trying to respect, each user is respecting the capacity constraint just for themselves. So it's possible that there's only 1 unit of toothpaste, I buy it, you buy it, somebody else buys it, and 3 units get sold. Okay? So given arbitrary prices, it's possible that some things will get oversold, some things will get undersold. And the Arrow-DeBrew theorem says that there exist prices which are going to clear the market exactly. So nothing's going to get oversold, nothing's going to get undersold. Or if nobody wants something, it's possible that something is undersold, but nothing's going to get oversold. Goods are going to clear exactly. Yes, in the knapsack problem, there was no allocation. So in the knapsack problem, my utility depended on the entire, so here I'm taking each good, I'm splitting it across many people. So either you get the toothpaste or I get the toothpaste. The knapsack problem is not really an allocation problem in the sense of, it's not a cake that I'm splitting across, that I'm splitting across multiple people. Oh, so each user is solving a knapsack problem. Sorry, each user is solving a knapsack problem. That's correct. Yeah, yeah. But the overall problem is not a knapsack problem. Yeah, yeah. So this is basically each user is solving the fractional knapsack problem with these prices, and then when you stitch them together, it comes out to be the solution. So it's a very non-trivial why this exists. There exists a set of prices, yeah. So there exists a set of prices, okay, such that which clear the market. And so, yeah. So clearing the market means that if every user spends all their endowment, yes, every user spends all the money, and no good gets oversold. There might be some good which nobody wants. So that's a technicality, which is why I can't say that every good clears exactly. But if you were to assume that every good gives some positive utility to everybody, if you assume that all Uijs are strictly bigger than 0, then every good gets sold exactly, everyone's money goes away exactly, even though the people are not coordinating with each other except via these prices. So the only way I'm coordinating with you in any way is that you and I are seeing the same prices. There exists a set of prices. So let's say the solution to this, let's call this X star ij. The solution to this, let me call it X star ij, is the solution to this problem. Because so X, yeah. So X is the variable. So I'm saying X star ij is the solution to this LP. There exists, so X star ij is a function of P's. Given P, you can define X star ij, right, by solving this LP. And so clearing the market means that there exists Xij star such that summation over all I of x star ij is equal to 1 for all j, assuming that uij's are all bigger than 0. Uij is equal to 0 can lead to funky behavior. So every good clears and everyone's endowment gets fully spent. Okay. So maybe I should have just done this. So this is the formal definition of market clearing. So there exists Pj such that x star ij is the optimum solution to this problem. So users are responding optimally from their point of view to the price signal, and the market clears. Yeah. Arrow Debrew. Sorry? Yeah, that's the Arrow's impossibility theorem. Yeah. Yeah, so the problem that I said with Nash is also true of Arrow. I mean, too much stuff. Okay. So this is Arrow Debrew theorem, right? This market is called the Fisher market. Okay. So Fisher market is basically where you have linear utilities. Okay. And the proof goes via a beautiful program known as the Gale-Eisenberg convex program. And the Gale-Eisenberg convex program is the following. You maximize summation over all I of log of ui. This is the Nash welfare program again, subject to summation over all ij, summation over all I xij is less than equal to 1 for all j. So xij is the allocation. So you're saying no good gets oversold. You want to maximize the sum of the utilities, and ui is just the summation over all j xij uij. So ui is the utility that the ith guy gets. Xij is the allocation of good I that they get. You can't oversell any good. You want to maximize the sum of the logs of the utilities. This is again the same Nash welfare function. And if you solve this convex program, it's a convex program, you solve it, you write down the KKT conditions, the Lagrange multipliers end up being the prices. Sorry? No, not in this program. So this is just a convex program that I wrote. It's nothing. This is so what we had was a definition of a market, right? That was the prices were in the market. This is just a new convex program that I wrote. There's nothing in this convex program other than what I wrote here. There are no prices here. Does it? Maybe I'm not understanding the question. So I define UI, right? This is UI. So it's not a function of anything which is not written here. This is basically UI. Okay? So I write a separate convex program. This convex program, on the face of it, has nothing to do with the market. This convex program just says I'm going to allocate these goods to individuals, such as maximizing this Nash welfare function. Okay? And that's it. As it so happens, if I were to take the dual of this convex program, were to write down the KKT conditions of this dual then the Lagrange multipliers that emerge from that end up giving you the prices. Okay? So the way this Arrow-Debrew theorem is proved, at least for the Fisher market case, is by taking the dual of this convex program, which is called the Gale-Eisenberg program. Does this? What did I say? No, sorry, Eisenberg, yeah, sorry. Yeah, that would be too much, even for Heisenberg, to do both Marquez and quantum. Yeah. So I think this is, are there any questions about this? I mean, you could write down the KKT conditions, and but my worry with writing the KKT conditions is they'll only make sense to people who already know KKT conditions, because I can't explain what KKT conditions are. But if you already know what KKT conditions are, then you can just write the dual yourself. Sorry? Okay, maybe the first order conditions is solving the problem, maybe. Or the way I would say is write the convex dual of this, and you'll get the prices are basically the Lagrange multipliers of this problem are the prices. So there are two separate things. So in bargaining, you and I are bargaining. There's not necessarily a market, and this is a separate market. So these are like the two things I'm going to show how both these things can be adapted to social choice.
Couldn't this be now interpreted as a bargaining problem between the customers, where UI is basically, UI is my utility, and the constraints now define the set of feasible UIs. So this is in fact a Nash bargaining problem between the customers.
Assuming linear utilities. So the thing is, the Nash bargaining problem is very general. If we did not assume linear utilities, we did not assume any specific form of these. But because the welfare function ends up corresponding to the Nash bargaining objective, it is indeed true that if you had linear utilities and you had exactly these good constraints and you had two players, then this would be the same as a Nash bargaining solution. That's correct. No, so the question is, can you extend this to nonlinear utilities? And so this goes back to your earlier question about why the utilities are linear. The Arrow-Debreu theorem works for any concave function, any concave utility. So it could be, your utility could be any function which is sort of concave, and generally everyone believes that utilities are concave, with some minor assumptions about endowments being bigger than 0 and so on. Okay? The Gale-Eisenberg convex program, the fact that you can prove the Arrow-Debreu theorem via taking the dual of this program only works for linear utilities. So the simple proof of Arrow-Debreu and the fact that you can get these prices, the fact that you can clear these prices, you get these clearing prices via the simple program only works for, because as you can imagine, you take these, if these utilities were arbitrary, the duals would be very complex. No, there are many ways of doing it. I'm just saying the dual of the Gale-Eisenberg program gives you the prices for Fisher markets where the utilities are linear. For other cases, the Arrow-Debreu theorem is harder to prove. For Fisher, you just take the dual, and the Arrow-Debreu theorem for the linear utility case falls out. Yes. $1. So normally if each user had a budget, if each user had a different endowment, then that goes here. Yeah. So it does show up somewhere. Yeah. So there's no a priori connection. Okay? And this convex program doesn't really exist in the Fisher market case. This is like an artificial construction. So this is a part of the definition of the program. There exist prices such that for those prices, when every user solves this optimization problem, the xi star j's that come out have this property. Everyone spends their endowment and the market clears. Okay? That's the theorem. To prove that theorem, this is like a thought experiment. You write this convex program, which a priori has, on the prima facie, has nothing to do with the original problem. You take its dual happens to give you the prices. So you write down the dual, and the dual happens to give you the prices, and the complementarity conditions that you get out of the dual end up being these market clearing conditions. And so if you know how to, if you're like used to taking KKT conditions, taking convex duals, then it's easy. And if you're not, then it'll take like too much time to do it here. So what does it have to do with our setting? So I've started at 10:30, right? So I have like 20, 25 minutes. Okay. So I'm going to give you, I don't think I have time to do like full details. I'm going to just give some basic insight, right? So we want to do some kind of a voting in a complex space, and let's say the space is so large that I can't even vote. Okay? So instead of voting, we want somehow to be able to collaboratively come to some kind of a solution. Okay? And we want not just voting, but we also want some kind of negotiation, deliberation, and so on. Okay? So that's what we want. We want some kind of a protocol for decision making. So we want some kind of a protocol for decision making that leverages these negotiation-like ideas. Okay? And so we want this to be a mechanism, not just an algorithm. So instead of thinking of these purely as algorithmic problems, I'm now starting to think of them as a mechanism, as an interaction mechanism. And we want to be able to prove guarantees on the quality of outcomes under analytical models, right? So in particular, we should beat something like random dictatorship. Random dictatorship is like this one thing which is very thorny, because it's often very good. You pick a random person as a dictator and you ask them to make a decision, and in a lot of these social choice settings, a random dictator actually ends up being quite good. So beating random dictatorship sounds like a funny goal, but it's often like hard to achieve. And so somehow you also want the mechanism to have low cognitive load on users. You should encourage some kind of negotiation and deliberation. Okay? And so what we propose is this thing called sequential deliberation. Okay? So you take a set of agents, let's say n is your set of agents, you put them in an urn. You put all the agents in a box. Okay? And you start with some initial set of solutions. Let's say it could even be one solution. Or it could be like the ideal point of every agent. You ask every agent, what's your ideal point? And you put these solutions in another urn, let's say urn B. Okay, so you have two urns now. One urn has all the people, and one urn has all the so this has the voters or the agents, and this has the solutions that these agents have come up to this problem. We don't really know what the problem space is. It could be design a budget, it could be choose a committee chair. People have come with a solution. You repeatedly draw two people from this urn. Okay? And so imagine this urn has just one point, one solution in it. So these guys can now change the solution that's in the urn. If they don't agree, then ST goes back. Okay? There's something I do with my kids, but often I tell them, like, after I came up with this, I started doing it with my kids. When we're going out for dinner, I tell them before I hit El Camino and Page Mill, if you guys can both agree on where you're going, then we'll go there. Otherwise, you're going to go where I want to go. Yeah. So this is sort of like, that's the nice thing about Nash bargaining, because there's always an alternative. It gives them incentive to agree. If they don't agree, then like the outside thing prevails. Okay? So that's it. We're going to keep doing it for a long time. And you can show that at some point, because you're always drawing voters uniformly at random, the voter population is not changing. Ultimately, this solution in the urn goes to some stationary distribution. It's not, you're not going to get a unique solution. I mean, you're not going to go to a fixed solution, but you go to some stationary distribution. You want to analyze the properties of the stationary distribution. So the question is, how do we model the agreement mechanism? So there are two answers, right? One is for the algorithm or the mechanism. We don't model it. The algorithm is just like you give it to two people. If they agree, then you put the solution back. If they don't agree, then you put the original back. And you don't really, the algorithm doesn't really specify or care whether you're doing Nash bargaining or tossing a coin or doing something else, or choosing one of the winners and you just saying, okay, you decide. Okay? For the theorems, we're going to assume that they did Nash bargaining. Okay? Which is why I described Nash bargaining. Okay? So I'm going to skip what Nash bargaining is because we just went over it. And the results is on a class of decision problems called median spaces. Nash bargaining between agents U and V with ideal points PU and PV using disagreement outcome S finds the median of PU, PV, and S. Okay? And so it's like a handful to parse. So I'm going to again maybe explain this with a diagram. Okay? So let's assume that U and the decision space is something called a median space. So I haven't defined what a median space is here, sorry. So a median space is a space. A median space is a special kind of metric space where if I take 3 points x, y, and z, there's a unique point which lies on all three shortest paths. Okay? So between any 3 points x, y, and z, there's a unique point P which lies on the shortest path from x to y, from y to z, and from x to z. Okay? So a line is a median space. If I take 3 points on the line, then the median of these 3 points lies on all three shortest paths. Okay? A tree is a median space. If I take a tree, and let's say this is x, y, and z, then I start to move from x to y, and wherever the path from z hits, that lies on all three shortest paths. Okay? A hypercube is a median space. Any high dimensional space equipped with the L1 norm is a median space. Okay? So it's a fairly broad class of space. It's not as big as metric spaces. So in the last lecture, when I said that there will be some connection within the next one, I meant like instead of assuming general metric spaces, we're going to assume a restricted class of metric spaces. In particular, we're going to think of median spaces. So in a median space, if we are given agents ut and vt, and the solution is st, then the alternative that they choose is going to be the median of these three alternatives, which is basically defined as this intersection of these shortest paths. Okay? So if ut is the voter, vt is another voter, and st is the solution in this space, and we assume that all these solutions and voters come from a common common metric space, just like we did before. If we further assume that the metric space is a median space, it's either L1 or a hypercube or a tree or a line, then the median, the path that lies on all three shortest paths, that is going to be the output of Nash bargaining. Okay, so this is the only place where we use the fact that we are assuming something about the bargaining, that they're doing Nash bargaining. So ut and vt are the two random voters that we drew, and st is a random solution that we drew, and we are assuming that voters and solutions come from a common metric space. Yeah, it's exactly the same as that we had before, where in the last lecture we had distortion. We assumed that voters and candidates come from a common metric space, but then we knew who the candidates were. Here, I'm not assuming that this decision space is complex. It may not be candidates, it may be budgets or something more complex. Yes. Oh, sorry, I thought you had a question. Yeah. All the ST. Yeah, so you just give ST to them and tell them that if you agree, I'll put your point back, otherwise I'll put ST back. And then you can formally show that if this is a median space and if they did Nash bargaining. You cannot make them do Nash bargaining as an algorithm designer, but if they did Nash bargaining, then they would return the median. Yeah, so that's like that. So for example, let's say this is ut and this is vt. So let's just assume that these people lie in a two-dimensional space. This is ut, this is vt, and this is st. And let's assume that the distance is here. This is the L1 space. The chalkboard is the L1 space. Then while negotiating, vt will say, well, st is my outside alternative. If you don't agree with me, if ut and vt don't agree, then st will happen. So vt has more negotiating power. Does it make sense? Because the solution is closer to vt. So if they're doing Nash bargaining, then you can show that the outcome of Nash bargaining will be this point. If on the other hand st happened to be here, then the outcome of Nash bargaining would have been that point. So even though this solution is not there, this solution is like a third person who's actually in the room. And in a way, informally you can think of this third thing as weeding out extreme solutions. So if ut is a really extreme guy, then vt will just not worry about ut and just choose st. So first of all, we have this result that the median always gets found, and then there's some truthfulness which I'm going to ignore. There's some convergence results which I'm also going to ignore. The convergence result says that the chosen alternative, let's say we just have one alternative, it converges to a stationary distribution in order of 1 steps. So I mentioned that ultimately as you keep drawing ut and vt, this internal thing is going to converge to some kind of a stationarity. But you can imagine that it will take a long time, but no, it takes a constant number of steps for it to converge to a stationarity. Okay? Let me illustrate that at the risk of not getting the markets part. Let me illustrate.
So even if you had just 1 point, you're not going to get any sort of, say, almost sure convergence.
No, you only get to stationarity. Yeah. So the reason is because let's say there's some chance that you end up ut and vt end up being the same person. I mean, even if let's assume that these people are paired up, like for every person there are 2 people. Maybe husband and wife always vote the same way, and maybe like there's one husband and one wife in this thing. Right? So then you might end up picking the husband-wife pair, and they're going to make the solution, move the solution all the way to themselves. So you'll never get almost sure convergence. Did that make sense? Yeah. So the reason this converges to stationarity is, let's just get intuition from the line. Let's assume the underlying opinion space is a line. And let's assume that these are the 4 people that I pick in the first 2 steps, A, B, C, D. Okay. So I'm going to condition, I'm going to couple this, I'm going to do a coupling argument. I'm going to condition on the fact that A, B, C, D are the first 4 people I picked in the first 2 steps of this iteration. I'm not going to tell you what order I picked them in. There's some probability that I picked A, B, and C, D, A, B first and C, D next. If I pick A, B first and C, D next, then because of the median property, once A and B are done negotiating, the final solution is going to be in this space somewhere. And then once C and D are done negotiating, the final step is going to be here. So if I pick A, B first and C, D next, the final thing is going to be at C, regardless of where you started out. And so that gives you convergence to stationarity. Regardless of where you ended up, you're going to end up at C, and that you apply a coupling argument, so you converge in a constant number of steps. So there are 2 theorems here, which I'm sort of like, I've already hidden some things under the rug. I've hidden a full proof of stationarity under the rug, but hopefully you got some intuition. And I've hidden the proof that they'll find the median under the rug, which follows some Nash bargaining. And that's the only place where I had to assume Nash bargaining. And then we can show that if we have a median space, then this, if you look at this stationary distribution of the solutions here, they're going to be they're going to be 20% worse than the best possible solution. Okay. So we're not going to get to optimality because anyway we get a distribution here. But in expectation, the solutions in the urn are going to be 20% worse than the best possible solution. And the best possible solution is the one that gives you, that minimizes the distances to everybody. Okay. And once again, while the analysis uses the median space, the algorithm itself does not use the median space in any way. So the algorithm does not assume any knowledge of the median space or any structure on the space. We can show that sequential deliberation cannot achieve more than 12%, so there's some gap here. And random dictatorship achieves 2. Okay, so we at least beat random dictatorship. And but if you look at the cost as not being the sum of the costs, but the sum of the squares of the cost, then random dictatorship can be infinite, whereas this sequential derivation still achieves 3. So cost would be defined as, so once again, it's a little bit funny, the cost is going to be, the algorithm doesn't actually know the cost, the mechanism doesn't know the cost, but in the problem, the cost of a point of a solution is defined as summation over all voters V. Cost of a solution S is defined as summation over all voters V of the distance from V to S. And this distance is in the underlying metric space, which we assumed is a median space. So, so this is the cost. The squared cost would be, this would be the squared cost. This is the squared cost. And if you just look at the expected cost, then random dictatorship gives you 2 and our algorithm gives you 1.2 in terms of how close you are to the optimum. And if you look at the expected squared cost, then we get 3 and random dictatorship gets infinite, is unbounded. So random dictatorship looks like is doing reasonably well in the cost, but it's not doing reasonably well in terms of the variance of the cost. Because random data is just so, I mean, so this is sort of a, so unlike the other distortion measure side, we didn't really have anything else to compare it to. Maybe that's why. And random dictatorship itself is quite good. So in fact, this, yeah. So maybe your question is quite valid. Why not compare it to some other existing measure? Like why not compare it to say Copeland? Yeah. So we could have compared to something like Copeland, but Copeland we know would give 3. So if I just ask everyone to rank all the alternatives in this median space, Copeland would give me 3 or 5, 3. And so somehow it seems like random relationship is actually better than some other natural things you would compare against. So maybe I should have also mentioned some open directions here. In my mind, the biggest open direction here is the following, right? And I'm not quite sure whether it's a theory problem or a systems problem. Somehow there are lots of mechanisms for voting, but there isn't really any mechanism for I don't know of any platform for deliberation. And so somehow when people talk to each other, right, they do some horse trading. And none of these current voting methods that we talked about take that horse trading into account. And the question is, can you design, and so can you design a system where people can themselves do this horse trading and come to some kind of a consensus decision? And the other very interesting thing would be to somehow model the fact that when I talk to you, my opinion changes. So whatever was happening here was pure negotiation. I'm doing Nash bargaining with you, but my opinion is not changing. But can we somehow also model the fact that when I'm doing, in the process of doing Nash bargaining with you, not only am I coming to some kind of a bargaining solution, but maybe my opinion is also evolving because it's being influenced by your opinion. So I think the open problem here is to make a model which is jointly a model of both opinion formation and bargaining, and analyze in that model and see if we can, somehow I feel like instead of trying to beat the 20% for our exact algorithm, I think the right thing to do is to try to see if we can jointly model bargaining and deliberation and opinion formation in a way that's well supported, is well justified. Just like the bargaining model is very well justified, it's like Nash bargaining. Then can you come closer to optimality? And then can you implement it, and then can you deploy it? So I have a feeling I'm not going to finish the markets part. So I'm not sure whether I should start or just have a conversation. I think maybe it's better to have a conversation about whatever we talked about, because I feel like what I talked about were more like theorems and mathematical statements, and some of them may not be. And I feel like just a conversation would be more useful for 5 minutes as opposed to going to markets. So I'm going to stop. Yeah, go ahead. So the question is like, so I made this claim that it would be good to design this thing and develop it and apply it. So we have done some user studies. And so the user studies where we did was we built this platform, and we did things like we asked people to choose 5 things out of 10, but collaboratively. Also, the question is, can it be used to solve a free rider problem? Yeah, I don't think so. Partially because things like the free rider problem, the way you're describing it, is mostly like an allocation problem or more like a cake cutting problem, in the sense that if A goes first, A benefits. If B goes first, B benefits. I understand. So I think in principle, there's no reason why you couldn't apply these techniques, except that for allocation problems, where one person benefits at the expense of another. Those problems have been studied ad infinitum, and the techniques for those kinds of problems are very advanced. So if you think about, say, bandwidth allocation, you'll probably find like 40 papers on TCP/IP bandwidth allocation, just on that alone. You think of packet routing, there's like a 50-year-old literature on fair packet routing, fair queuing, right? So generally in problems where people are you're giving differential treatment to different people, those problems, the fairness, allocation, game theoretic aspects, they're well beyond anything that I'm talking about. And what we are doing here is sort of like, you can think of this, the allocation field like 30 years ago before Kelly's work on proportional fairness. And so I'm not very optimistic that we are going to come up with that these techniques are going to be useful in a literature that's been studied for like decades. Whereas the difference here is that you have to make a joint decision. And even though you would have thought that public decision making is an important problem, in fact, you could arguably claim that right now the biggest problem, the biggest bottleneck in the world right now, if you have to pick a single bottleneck in the world, is people being able to make consistent decisions. Forget even about good decisions, just consistent decisions from like year to year, year to year. For example, in San Francisco, which is very close to where I live, everybody complains about the housing problem. But you pick a random person, and the random person has 3 thoughts at the same time. The first thought that they have is, because I'm very liberal and very compassionate, I want all the poor people to be able to stay in the city. The second thought that they have is, because I'm an environmentalist, I don't want to build. And the third thought that they have is, because I work in the valley, I want the valley people to be able to come and live in San Francisco. So it's not even that they have an ideology, it's that they're not making consistent decisions. And people's inconsistencies are reflected in politicians' inconsistencies. And so even though I feel like being able to make good consistencies is the biggest problem, somehow the understanding of that is very far behind. So I'm not, the problem that you're describing is important, but it's like very well studied. The kind of free rider problem that this could solve a different kind of free rider problem. Let me illustrate the kind of free rider problem that this could solve. I know it's a long answer, and I'm going to go to my market analysis after all. Okay? So let's imagine that you were to design a market mechanism of public decision making based on this private goods idea. So you could say something like, here's how you would design a market. If you were to make a Fisher market for public decision, this is what it would look like. You assume there are many, many issues. Instead of goods, you have issues. Let's assume these issues are divisible or randomized. Each issue has a price. So this is the only thing that will change in like, well, there's going to be no other model. And each player is given $1. So instead of goods, you have issues. Each player still has $1. But this player can use a budget to buy probability. And you can buy the probability on this side of the issue or that side of the issue. So if an issue has price P, you can spend P dollars to buy 1 unit of probability here, or P dollars to spend 1 unit of probability there, whichever side you want. So let's look at an example that happens. I have a minute, I'll take 2, and I'll finish this in 2 minutes. I think I'll finish this in 2 minutes. Okay? Let's look at this simple example. Okay? In this simple example, so this is sort of my attempt, this is the first attempt to try to take Fisher markets and apply them to public decisions. Okay? You have these issues, and let's assume that on each issue, one player is on the minority side, everybody else is on the majority side. So on issue I, player I is in the minority, and everybody else is in the other side. Okay? And let's assume that player I has weight 1 for issue I. So when you are on the minority, you have weight 1. When in the majority, you have weight 1 minus epsilon for some very small epsilon. So it's not like you hugely care about the issue when you're in the minority. It's not like building wheelchair ramps for handicapped people. It's more like I want to have pizza versus burger. And so by symmetry, all issues will have the same price, and you can solve the equilibrium. And the equilibrium turns out to be that for every issue, the minority decision will end up happening. Okay? And that's an example of the free rider problem here, because what happens is you don't want to exert effort on behalf of the majority, because on the majority side, you want to be a free rider. So nobody exerts any effort on the side of the majority, and therefore the minority issue happens. And people in democracy often worry about tyranny of the majority, but there's another issue that happens if you start to think of a market-based approach, is tyranny of the minority. And it might seem like this is just academic, but I actually feel like this is something that does happen. And so what happens, at least in the US, where I understand the politics a little bit better, what happens is that the way people can exert influence on politics is by calling their congressman or congresswoman, or going and rallying, or donating money and so on. And they choose to exert that effort on behalf of minority issues. And by that, what I mean is, for example, you might think that good health care for the elderly is a very important issue. It's very important for everybody. But it's very important for everybody, so nobody exerts effort on that behalf. But maybe gun control is an issue which is important to only a few people. So they put all their effort on gun control. Sorry? No, the minority of the people who are on the NRA side give their money to the NRA, as opposed to no. So other people, there's another minority issue. So if you're on the left side, you might put a lot of effort on transgender rights, which may not be the most important thing for you. Even for people on the left, maybe other issues are more important than transgender rights. But they'll agitate on behalf of the transgender rights, as opposed to agitating on behalf of bigger issues which may be more important to them. So this is where the free rider, so the free rider phenomenon here comes a little bit more subtly when you try to design a market. And then I don't have time to go into it, of course, but what I would have talked about if I hadn't gotten derailed is to show you like a redesign of a market which could maybe address some of these issues. Okay? But I am happy to take that offline. So thank you very much for giving me the chance to come and talk here.